over to you.
Okay, thanks very much, Krasi. So we're switching to gene regulatory networks and perhaps biochemical kinetics. I'll talk about that a little bit at the end. So this is actually joint work with Graham Quee, who is a master's student funded by the Natural Sciences and Engineering Research Council of Canada. Let's see. Okay, so briefly, I'm going to talk about qualitative models of gene regulatory networks. Traditionally, these have been done by step function interactions. This is what's known as glass networks, but I'm going to suggest another way of approximating the control functions as ramp functions. We'll talk about solutions in 2 dimensions to begin with, and then go to n dimensions and look for these maps in phase space that allow us to solve for actual trajectories of solutions in explicitly in the same way as we do for glass networks. I'll talk about some more restricted classes of systems where we can do a bit more, and in particular negative feedback loops. So the idea here is really qualitative models of you have your gene network where one gene will turn on or off the expression of other genes, or perhaps several genes, the products of several genes in combination will turn on and off expression of other genes. So you can get complicated networks of logical forms of interaction, taking the form more or less of Boolean functions that if this is present and that is absent, and this one is expressed, and so on. Often you don't know the parameters, the rate parameters of all of these things. And so Leon Glass many years ago proposed this sort of qualitative model where you just simply describe the concentration of a protein product of a gene by this differential equation, which has a degradation term because these proteins do degrade over time, and a production term, this is the gene expression, which depends on what I've written here as x tilde as a vector, which is the state, the on or off state of the other genes. So in concrete terms, that means whether or not the protein product of the gene is above or below some threshold concentration. Now, this is unrealistic, of course, and nobody ever thought that this was exactly right. But the idea was to try to develop a kind of a systems theory of gene networks so that you could say, if you have such and such a structure or wiring diagram, what kind of dynamics do you expect? And because of the fairly simple nature of these equations, in particular with this sort of piecewise constant reduction term, piecewise constant because things are either above or below, so the values here are 0 and 1, then you can actually explicitly calculate solutions, and that enables you to prove things about existence and stability of fixed points, periodic orbits, and even more complicated dynamics. So these binary on-off functions are, of course, an approximation, a rather crude approximation of some smoother kind of switching function, which typically is modeled as a hill function like this, with some exponent that determines the steepness. So we're taking a smooth hill function type interaction and approximating it by a step function. So as I said, this enables you to do calculations. As long as you're away from the threshold values, then the production terms have, in each variable, have one of, well, 2 to the n possible values, just because there are 2 values on off for each gene and n genes, so there are 2 to the n possible states of the system. And in any box in phase space, by box I mean a region above or below threshold for each variable, we have a very simple differential equation, and we can solve it explicitly like this. So there's a focal point coordinate for this variable, the ith variable, and exponential approach towards it. So the focal point, if we put all the variables together now, for some particular box J here, is just a point in phase space, and the solution to this system is simply exponential approach to this focal point. Either asymptotically if the focal point is in the region where it applies, or until you hit some threshold and something switches, and then you have a different focal point, and so on. So in the simplest case, which I'm often going to use, we'll just make the degradation rates all the same. That's of course also not biologically realistic, but it makes mathematics a lot simpler. And much of what we do in that case can be generalized anyway. So just to keep things simple, I'll sometimes do that. If we're going to make them the same, we can rescale things to just make them all one. And then we get fractional linear maps between threshold crossings, which are called walls often. And so in pictures in 2 dimensions, it looks something like this. So the S plus and S minus here are increasing and decreasing hill functions, or step functions in the limiting case. And the flow in one region, say both variables above threshold here, is towards some point in phase space, a focal point, until you reach the boundary. But then of course you have a different focal point. So in this box, you go to some other point, and the flow is towards the differential equation has the form constant minus constant times x, so it's simply exponential approach towards this value. But then some funny things can happen. You can get a possibility of more than one variables could possibly switch first if I'm in this box, depending where I am. Either the second variable could cross its threshold, or the first. So there can be more than one sequence of transitions. Also, we can have the flow towards a wall or a boundary from both sides, and these are called black walls. And the flow then becomes stuck in this threshold region, and then you have to deal with this sort of singular situation where there's flow along this threshold boundary. And even worse, it could get stuck at a threshold intersection, and then you have to figure out what happens at these threshold intersections. So yeah, that's what this says. So black walls and intersections of multiple thresholds. And then you can use singular perturbation techniques, because really we think they're sigmoidal and not step functions. So you perturb away from the step functions to find out what happens. Or you can use Filipov methods as another approach to assess the dynamics from in those threshold regions. So just as an example, this one is from a classic paper by Plahte and Kjøglum. So here you can see that there's a product term. So it takes the presence of the protein product of both the first and the second gene to, well, repress, in this case, the activation of the first gene. And similarly here for the second one. So in this particular structure, the Zs here are these increasing hill functions. With some set of parameters, we can get flow like this. So here the flow is towards a boundary on both sides, and we have a black wall here. Here there's also a black wall. But now if you look at flow above the dotted line, you hit the black wall on the vertical wall here and flow in towards the center. But if you're line, you hit the wall on the right here, and then you go out towards a fixed point in the wall over here. So things get a little bit sensitive. And if you do the singular perturbation expansion in the threshold intersection, for example, then you have to deal with equations like this. The terms in parentheses are the right-hand sides of the original equations, and these terms come from translating to the Z variables from the X variables. So you think of this as the hill function, and you invert or transform the variables, and then you change the time scale, and then you let the slope of the sigmoid go to infinity, and you end up with equations like this. So this is sort of blowing up the singularity at the threshold intersection, and in this case, you end up with a spiral point over here and a saddle point over here, and then there are these fixed points on the boundary. So these correspond. This one corresponds to the black wall the vertical black wall where you, in the previous picture, and this one is the fixed point in the black wall and the horizontal black wall on the other side. So depending where we come into this threshold intersection, we can either stop there at the spiral point, or we can get sent out to this other fixed point over here. Now, these kinds of things depend to some extent on the step function interaction, right? I mean, really, they're not infinitely steep, they're finitely steep. So to what extent does that influence things? So there's a whole theory of glass networks, and you can do lots of analysis, and it's all very nice. But the biggest objection has always been that really these interactions are not infinitely steep. So what I'm suggesting here is, what if we approximate these smooth sigmoidal functions by ramp functions instead of step functions? We still have piecewise linear control functions. And so maybe we can do some of the same analysis, but we won't have this sort of infinitely steep problem, discontinuous right-hand sides and singularities and special methods to solve those systems and so on. So instead of a binary control function, we're now going to have a ramp interaction function. So the binary one was a tilde on top, the ramp one has a bar on top. And we're also going to use, now we have two thresholds. So there's a theta, which is the lower threshold. This form of the phi variable here is the upper threshold, and m will be the midpoint of the two. So in the example that we looked at before, we can write it as a system, something like this. I've actually taken a bit of a liberty here to make the decay rates the same, although I've divided by them here so that the focal points are the same as they were in the original system. That doesn't really change anything important. But so here, if you look at the middle picture, you can kind of see what's happening. The red and blue curves are the nullclines of the right-hand sides here, or these two variables. So where they intersect, there are fixed points. And so here you can see the spiral point, which is inside the central box, the threshold intersection, if you like. There's a saddle point here, and there's another fixed point over on the right, which is in this sort of what was a wall and is now a threshold region over on the right here. As I increase the slope of the ramp function, I go to the right here, and things just become tighter, and in the limit, this approaches the step function again. But if I decrease the slope of the ramp function and make it wider, so the threshold region is getting bigger, then I can lose some of these fixed points. So here, the red nullcline and the blue no longer intersect. So I've lost the fixed point over on the right and the saddle point, and everything now goes to the spiral point. So this kind of shows some of the things that can be misleading about this glass network approximation, that if you have infinitely steep, that's not actually what may be going on. If the slope is somewhat shallower, then the dynamics may be different. And this still simplistic approximation allows us to sort of tease out the effect of the slope of the interactions. So how can we do the kind of analysis on this ramp function systems as we did for glass networks? For glass networks, we often shifted the thresholds to 0. Here we have 2 thresholds. So what do? We can make any shift we like or not, but common useful shifts are the first threshold or by the midpoint, typically. So solutions to the system inside each of the boxes. So we're in some box for each variable here. Ri is now going to refer to the ramp region. So that's the region between the thresholds. So if I'm in the intersection of the two, that's the central region in 2 dimensions. If I'm outside the central region, then I have an affine form of the differential equation, no product terms. The product term could come about from being in both ramp regions at the same time. So outside this, the central region, explicit solutions can be found in the usual way. The psi here is the fundamental solution of the homogeneous system. The B vector here is made out of the focal point coordinates for this region. If I'm in a corner region, then it really is the same as for glass networks, and you just get this exponential approach towards the focal point. And then you can calculate explicitly when a threshold is crossed, because you can solve for t here when x equals the threshold value. Well, one of the xi's is the threshold value. And so you can calculate the time of the crossing and so on. If we're in a region where one variable is not in the ramp, that's the ith one, and one is in the ramp, that's the jth one, the system still has an affine form, but various things can happen. It depends on whether the focal point changes across the ramp, the focal point coordinate in each variable. So we can get solutions that have this form. So you've got a t e to the minus t term and an e to the minus t term. Or in another situation, the ramp variable itself may have just an exponential term, but the other ones may have a combination of two exponential terms. So the problem with this S2 type solution here and this S4 type solution here is that you can no longer solve for t, setting the xi to be the threshold value and finding the time of the crossing. You can no longer solve explicitly. I mean, of course, you can do it numerically. So this makes analysis a bit more difficult, but we can for the ramp variable itself. So if the one variable that's in the ramp, if it were to go straight through the ramp and come out the other side before anything else crossed, we would be able to calculate that crossing time. In the central region, where both variables are in the ramp region, then we can't necessarily get explicit solutions, but the form of the system is this. You can write down the nullines, find equilibria as a solution of a quadratic, and calculate the Jacobian and find stability. So this is the kind of thing that happens. I showed you this picture already. Spiral point, you can calculate the saddle here and the fixed point here and so on. This is a 2D periodic solution just to show that some funny things can happen. Here you get I'm kind of rotating these focal points. They're a little hard to see there from one diagram to the other. They're rotating. And there's a bifurcation that happens where you go from a stable spiral point to a large periodic orbit. And actually, the periodic orbit is instantaneously large. At the bifurcation point, you get a series of nested periodic orbits inside the central region, the biggest one being the biggest one that fits. And after the bifurcation point, you have something, a bigger periodic solution. So it's not exactly a Hopf bifurcation, but in a way, this is an artifact of the ramp, the linear part of the ramp. For smooth systems, you actually have an ordinary Hopf bifurcation here. We can calculate these ramp-to-ramp maps as long as we're only in regions where we're only in one ramp at a time. So this corresponds in glass networks to where you have only one variable at threshold at a time. And you can do it because one variable, the ramp variable itself, you can solve for the time of crossing. So you can actually determine whether the other one is going to cross first or not by solving this one for t and then plugging it in here and seeing which side you're on. So I don't want to go into this in great detail because I don't have time, but it involves sort of some tests about this exponential term and linear term, and you have to compare them, and you can do that from the time of the other variable. So there's a theorem you can write down that tells you whether you go through the ramp region or whether you fall into a double ramp region. You can write down the maps for the equal degradation case. They're these sort of piecewise or these sort of fractional linear things. So it's similar to what you can do for glass networks. This is sort of hinting that we can find out things about periodic orbits. So we can do explicit calculations as long as we stay in the single ramp regions and don't go into a region where more than one variable is in the ramp at the same time. But what if we do? Then it's harder to figure out what's going on. So then we need a sort of a more general theorem like Hastings et al. For smooth systems. So I just want to talk about that briefly. I'm going to skip this, for affine systems, so if the system itself is affine, as is the case, for example, for a Hopfield network type system, then everything is explicitly calculable and there's no problem. But let's look at negative feedback loops very briefly. So I'm going to set it up so that all the interactions are positive except the one from the nth variable to the first, which is negative. You can always translate variables to get it into that form. So there's a famous paper by Hastings et al. From 1977, which shows the existence of periodic solutions in such systems if the unique fixed point in the center is unstable. But it depends on the system being smooth and smoother than ramp functions. The saturated parts of the ramp functions make this theorem not apply. And it's actually not trivial to adapt it to the ramp function case. But we did this, and you get these sort of, if we shift it by an arbitrary amount, we get these affine things, and the idea is to find a shift that makes the constant matrix here 0, well, piecewise constant matrix in each box. So we basically shift to the equilibrium point. I'll skip the details here, and you can show that the unique equilibrium is unique. And so you end up with a system where U is where 0 is the equilibrium, and then you have to show that for this kind of negative feedback loop, if the origin is unstable in the all ramp region, then there's a non-constant periodic solution. And Hastings' paper has a set of 22 lemmas. It's quite a non-trivial theorem with a lot of topology and so on, and we had to sort of adapt it to this case. It involves essentially 3 steps. You basically show that it follows a sequence of boxes around the cycle, which could, in principle, spiral in towards the origin. But then you show that it doesn't if the origin is unstable. There's a cylinder in the middle that you have to stay out of once you're outside of it. And then you have to show that there's a cross section of this, this set of domains, so like a Poincaré section, outside of the central cylinder that's topologically an n-1 dimensional cell, which is topologically equivalent to a ball. And then you can apply Brewer's fixed point theorem. So that's the idea. It's to show that it's non-trivial. This is sort of in a 4-dimensional network. This is a 3-dimensional cross section. And in the original Hastings paper, you just had a simplex, but here you have the sort of non-shaded part of this prism region here, and things get a little bit tricky to show that it all applies, but it can be done. So there are limitations here, of course. This is only existence, not stability or uniqueness of the periodic orbit. We've done everything with equal decay rates, although that can be extended quite easily, I think. There's a question about what ramp best approximates the sigmoid, but in a sense, this is just qualitative modeling anyway. And more complicated logic makes things more complicated in multiple ramp regions. So just to sort of sum up, we can do much of the analysis we could do for glass networks, at least in these sort of simple settings. It's sort of promising way and a more realistic way of approximating network interactions. And then we're going to be looking at Michaelis-Menten kinetics as well. That's another talk, really. Thank you.
Thank you very much, Rod. I don't see any questions in the question and answer box, but I have a general question. It's very interesting work. So has anybody done a systematic comparison of these dynamics in the case when you're using like the switch-like or infinitely fast transition, or the more gradual, like you're approximating with the piecewise linear function, in terms of dynamics, possible dynamics, I guess.
Yeah, so there's been, for glass networks, there's been lots done. And yeah, you can, I mean, the nice thing about the sort of analytic tractability of this class of systems is that you can even do things like prove chaotic dynamics, strictly speaking. And you know, what the relevance of that is to gene networks is not so clear, but it does turn out to have applications in electronic networks, which can be used in cybersecurity systems and things like that. But yeah, so you can do a lot of analytic work on explicit kinds of dynamics to show existence of all kinds of dynamics in this class of systems. But that's for glass networks. So now I'm suggesting that we try to do something like this for ramp network systems, which are actually more, you know, more reasonable approximation than step functions for gene networks. I mean, you could say, well, why not do it with hill functions? But and some things can probably be done, and there are papers on that too. But it's these are highly nonlinear. You know, you can have products of terms here, products of hill functions, and so on. Things can get quite difficult to analyze in the full complexity of that setup. So ramp systems have the advantage of being piecewise linear, and my hope is that we can do more analysis.
Yes, yeah, that's. I fully agree. I fully agree. I was just more wondering whether there are things that you can lose or gain using one or the other framework, but I guess as these things progress, we would be able to say how these, yeah.
Yeah, certainly glass networks give some misleading answers sometimes, and this is what I hope to show here, yes.
Thank you.